It's a great pleasure to be back home. I even used to be a professor in this institution for 5 years in the early 50s, so I feel very comfortable here. And I appreciate the nice audience, including some of the more important people around here. I'm going to tell you a story first about how a building got designed, which I think is one of the more important buildings in the world, if I may brag. Some evidence of that is that I just got a communication from Paris 2 days ago that they want me to help them put out a complete description of this building to be shown in the Pompidou Museum in Paris in June of 1997. And they're going to exhibit famous structures of the 19th and the 20th centuries. So this is, I hope, you will find it interesting building. Now we're going to start out with some slides, and I'm going to lead you up through the creative process and then tell you about a few things that went wrong. So we will start out with the first slide, and this is the first 50-story building built in the world out of steel frame in New York City in about 1910. It is the Metropolitan Life Insurance Company building. I show you that because the whole tradition of building tall buildings was quite advanced a long time ago. The technology of making rigid connections between steel members was well developed, and people were quite confident. And 20 years later, then they built another tall building, which is the Empire State Building, which you can see in the background. And for scale, the one I showed you first is in the foreground. So there is what happened: 50 stories, 1910, 100 stories in about 1930. Something just fell on the floor. Anybody want to put that back on my belt again? Anyway, that's the Metropolitan Life, that's the Empire State, and that's what the Empire State Building looks like at night. There are a few other famous buildings, but we haven't the time to discuss them. All this technology of wind engineering and so forth, controlling the motion of the buildings, was all fully developed. By the time the Empire State went up, people knew that you designed a building to control its motion, so people are comfortable. Now, there was a big gap during the 30s and the 40s and so forth, and people didn't start building again until the 1960s. And the first real innovation in tall buildings, I think, could be said that this was one. And it was famous because a great engineer designed it named Fazlur Khan, and great architectural firm, Skidmore, Owings & Merrill. But the innovation in this building was the fact that it abandoned all the rigid frames and used diagonal bracing in the building and made an architectural feature out of it. You can see these great diagonals running up and down here. This is the John Hancock building in Chicago, and it certainly has a gutsy quality to it, I think. I think the engineers of the world really admired it. Anyway, this building has never been copied because some people find it, I think, a little too un-architectural. I mean, it isn't very loving, but nevertheless, I admire it. Well, this building influenced me greatly. I started designing tall buildings in Boston. This was my first, it's still there, it's the State Street Bank downtown, but it was the first thing you could call a skyscraper that I ever worked on. And I did it in the same tradition as those earlier buildings. It did have some unusual aspect. It had all these long cantilevers at the edge of the building. All the floors were cantilevered out 17 feet so that you didn't have columns at the edge obstructing the view. Another building that I have done here in Boston, and this was in the early 70s. You may have seen it downtown. It's the Federal Reserve Bank. This begins to get a little bit unusual. There's a hole through the whole building, which you can actually fly an airplane through there from one side to another. I think somebody even did it once, but But this is a building that has a huge span. The whole building spans from one end to the other, and these two towers at the end hold it up. Now, the architect for this particular building was a man named Hugh Stubbins, a very famous man in America. And he had done some buildings for MIT, Harvard, everywhere around here. He hadn't done too many skyscrapers, but this was really his first important one. Anyway, he was picked to do a very unusual building in New York, the CityCorp Tower. And we're now going to see his first rendering. This is the arrived at after about a year of study. The whole problem was to build a building on a site that has a church in one corner down in the back. And the church owned the land, and they had a crummy old building. Nobody wanted to save it. It was the lowest point of Victorian architecture, but they wanted to have a new building on the same site. So they negotiated a deal with the bank that they would sell the air rights, the whole volume of space in one corner of the building, and the bank had to develop a structure that would not penetrate that, but it could hover above. So this led to the unusual configuration of the building. You couldn't have columns in the corners where they ought to be in a conventional building, so they were moved to the middle. And this was my suggestion, to say, let's just have one column on each side, and the building will then be symmetrical. And now we have to find a way to build it. I started out thinking about building a table here and then putting a conventional building on the top, but that seemed like the easy way out. It was also the most expensive way out. And there's another view of the building finished. But let's get back to some brass tacks. That's another view of the building finished on the side street. You can see there's quite a bit of scary excitement there when you walk around the corner. And here's the church. Actually, we did the church too, the same architect and engineer team. The church is a rather nice building, especially inside. It's I don't know what those cars are doing there. This is during construction, so it wasn't finished when that picture was taken. But the church is floated on neoprene rubber, believe it or not, because the subway Lexington Avenue line goes down the street, and it would make it absolutely impossible to have a quiet service if you didn't isolate the sound. And that works quite well. We're not going to talk about the church further, but now you look at that, and it looks kind of bland. Actually, the architect wanted to keep the building simple in its skin because there was so much drama going on at the bottom and at the top anyway. He said, no, if you're going to have any diagonals, I don't ever want to see them. So anyway, in the middle of the building, the elevators do come down to the ground, and there's a very powerful stem there, like a stem of a mushroom, that keeps the building sheer, under control, and has a lot of solid steel diagonals. But this is the diagram for the structure of the outside. This was something you laugh at me, but I did conceive it on a napkin at a Greek restaurant in Cambridge. And the thought process went like this, that if we're going to have a big column at the bottom, why don't we just run the big column all the way up and pick up the loads of gravity coming down in increments and guide it down to the center column by a diagonal in compression. And what you see here is a set of super modules, you might say, 8 stories high. Loads come down there, are picked up and brought back, and there's another secondary load, actually the bigger load right there. Anyway, the loads are all gathered up and put and concentrated into one main column. Now, this is a very efficient cantilever. If you make a bracket with that proportion, it's an ideal, actually. It's a mathematical ideal. So if you have to hang a building out what is actually 76 feet from the center, this is a good way to do it. But the other thing about those diagonals is that when you wrap them around the corner, and you have to remember all 4 sides are identical, they all connect at those points, and they form a triangulated tube or a structure that is 3-dimensional and is able to take the wind across the building. Now, these are some pictures from construction. You can just see some of this going on. These are diagonals coming up there. I can't quite see it around the corner, but it's there, and so forth. I think the next picture is a little bit better. And there's some peculiar things going on here. We were picking up these loads and bringing them down here on this corner, and in order to make it behave the way I wanted it to behave, I made sure that it couldn't go down any further by just simply leaving the column out there. That solved a nice architectural problem, too, because if you have three members ganging up in the corner, it's kind of a nasty experience when you're inside trying to see out. In this case, you've got mitered glass around the corner. Now, while we're at it, let me say something about the engineering of these diagonals. The strains in those members are very important contributors to the overall deflection of the building. And this building is over 900 feet high, so the engineering to control its motion is an essential part of the design. And you can't use high-strength steel in small members. You need a lot of cross-sectional area and a lot of material, so the strains will be low. This particular structure happens to get strained on when the wind is blowing straight on the building. Even the diagonals in the plane perpendicular to the direction of the wind are strained, so they're kind of an extra demand. So these members are actually quite oversized in the relationship to normal steel stresses. When the building was drawn up and all the final drawings were set, and we had a joint venture partner in New York who made some of those drawings, they were very, very conservative, and they called for these members being made with full penetration welds from time to time. You can't build a diagonal going up 8 stories and put it up in one piece. You've got to put it in sections. So there's a joint there, and then there's another joint down there, and so forth. And there are 5 joints in every 8 stories in every one of those members. And they were called for to be welded. And I knew that because I saw the drawings finished. The top of this building ends up with a lot of construction up there, which I'm not going to try to explain. It was architectural reasons. It does have a lot of cooling towers up there. The form got generated initially by planning apartments facing south, and that was an uneconomic idea. So, but the form survived. This is where the floor where the window washing machines come out, and this is the last office floor. But up in here is some remarkable things going on. Now, one of the amazing things about this building structure, that's the view up there during construction, it's rather nice, is that it's so lightweight that when the wind blows, it is more dynamically excitable than a building that weighed twice as much. And we knew this was likely to be true. Now, of course, we had the most sophisticated wind tunnel tests available in the world up at the University of Western Ontario. And a previous building that I had worked on that never got built, that was to have been in New York, led me to think about a similar problem and to solve the problem of the building's excessive motion by an enormous damping device. So this time we were ready, and we did tests of this machine called a tuned mass damper in the models that were tested in the wind tunnel. Here's the kind of, that's a little out of focus to me, but anyway, this is a map of New York and shows you within that circle the area that would be modeled in detail in the wind tunnel. That's at a scale of 1 to 500, and since this is a 8-foot diameter on the model in the wind tunnel, it's 4,000 feet diameter circle. And every building in there is modeled to scale because they all influence each other. That's our building in the middle. This can be rotated, and you could figure out what the wind does from any direction. This is what the models used to look like. They don't anymore. They've simplified the process, but this was a model that pivoted and was built to be to dynamic scale. I mean, everything was scaled properly, so the building actually moved. And with these sensing devices down here, and one thing and another, you could measure the actual mechanical response and get the forces on the building. Out of that would come data of this sort. People always want to know how much a building moves at the top. Well, there's a chart that would tell you. If you don't do anything special to the building and you have a natural damping, which is as low as you might get in a steel building of 0.5%, 0.05%, 0.5%, that's right. Anyway, this is a time return period of storm. If you took a 50-year storm, the thing would move not quite 2.5 feet. If you go to a 150-year storm, it's moved 3 feet. If you put a device in to change the dynamic behavior, you can lower these things way down. And this is actually what we ended up doing, is putting in something that achieved 4% of damping mechanically. Now, what's going on? What makes these buildings move? Well, when the wind blows head on a building this way, things are going to happen that make the building go perpendicular to the direction of the wind and oscillate. If you ever rowed a boat down a stream and saw a cattail in the moving water, you'll find it swaying back and forth across the stream. This phenomenon is called results from vortex shedding, which was figured out by the great German von Karman way back in about 1910, that if you have a fluid moving by an object that is symmetrical, you will get turbulence develop alternating on each side, and the time intervals of those turbulences forming, which are called vortices, they're like tornadoes up and down the building, can be determined, and it's a function of the dimension of the building, the density of the fluid, and the velocity. Now, if these things get near synchronous with the natural frequency of a building, you've got a serious problem. In fact, that's the ultimate design criteria. We weren't synchronous, but I'll show you this as an example of what it is that excites the building. If the building is excited and has no significant self-damping, it takes a long time for the vibrations to die out. If you put a tuned mass damper that has an enormous amount of damping and it dies out in a very rapid rate, and you combine the two, you control the damping time very effectively. Now, what does the tuned mass damper look like? Here's a plan of the very top of the building, and in that plan, what you see is a mass of concrete, which is 29 feet square and about 8 feet thick and weighs 400 tons. It is floated on pressurized oil bearings. In each direction, it is connected to two things, really. You'll see another picture of this, but this rig in there is a spring, believe it or not, made of pistons opposed to the direction of motion, but they move. Anyway, it's the compression of gas that is controlled beautifully by geometric devices to get it up to what we needed. We needed a spring that would go plus or minus 3.5 feet and have a force of about 150 kips. That's an enormous spring, a very complex design problem to work in both directions. You don't use a helical spring for that, I'll tell you that. Anyway, this thing can move back and forth this way, and then there's a rig to keep it from twisting. Here's a plan of all this, and I don't think you can study all this now, but I'm giving you all a little handout later on, and then one of the pages in there, you can study this machine in a little more detail if you want. This slide, I really apologize, it's got much too much information in it, but you get the sense. Let's look at the real thing. There's a model of it again that was made by the manufacturer. Incidentally, how did this get made? I had some very good advice from a lot of people. One of the great advisors was the man who gave me the idea in the first place, which is named Professor Robert Scanlon, who's a great man in the history of dynamics. and vibration control, particularly bridges. He's just ready, he'd retired finally from Johns Hopkins, where he has been for the last 12 years, but he was at Princeton at the time I met him, and he told me all the principles of tuned mass dampers, and he said, I don't know anything about buildings, you'll have to go on your own after that, but he guided us to the literature, some of which was written at MIT, of course, theory of random vibration. Anyway, the final development of this came out by us figuring out what we needed and what the scale of it was, and then having a performance specification and seeking some proposals from manufacturers. A great man who was a mechanical engineer, I think he was even head of the department here one time, named David Wormley, was the principal consultant who advised me to seek hydraulic bearings on this thing and hydraulic springs. We had talked about all kinds of ball bearings, and he said, you don't put a thing like that on ball bearings. You put a locomotive on ball bearings, you got to exercise it every day. Did you know that? The bearings flatten. Anyway, this floats on grease. We went to a manufacturer and came up with a wonderful company in Minneapolis named MTS Systems. And there was a mechanical genius there named Neil Peterson who developed these extraordinary devices, which are the springs. And if you look at this thing, this point's going to move back and forth. And we've got two opposed pistons here. They're pre-charged with nitrogen gas. Now we move this thing, and they move neither one direction or another. Well, the force that moves it this way is only a component of the force going on in this thing. But it turns out that when you combine these dimensionally, superimpose the two actions of going this way, and take into account the nonlinearity of the compression of the gas, you end up with a more or less linear spring. I mean, this is what we wanted. I think it's absolutely one of the most ingenious mechanical devices that I've ever seen. That's what it looks like. These are the cylinders opposed. This thing rides back and up. Now there's a thing called an actuator at each end, which is essentially a dash pot, except it's a very sophisticated one with sort of feedback mechanical valves that keep the pressure going. Well, what does this thing do? There's a picture of it standing there. This black hole there is nothing but black oil that it's floating on. But we'll see another picture in a minute. This rig keeps it from twisting. If you look very carefully underneath, you can see these silvery discs. There are 16 of them, and they have oil pumped in and a pressure there that levitates the mass and makes it available to start moving freely when it needs to. Most of the time, it just sits there. There are devices on the building that measure accelerations constantly, and only when you get a background level acceleration of 3 millig's does there a sign that a wind's coming and it might come on. This thing here is a safety device, and they're all around the edges of it. In case something breaks and the thing has moving at full velocity and has an enormous momentum, it would cause a lot of trouble. These two pictures show you the amplitude of motion. These were taken during an initial installation of it all back in about 1977. And the thing is being exercised and forced to move. So here it's leaned way over as far as it goes, and this thing has to lean to follow it. And then this picture, it has gone all the way the other way, and this thing is leaned back. And this has been deliberately crashed to test these snubbers. The snubbers are the same kind of thing they use to dead-end railroad tracks and railroad stations, because if the locomotive breaks loose, you don't want it crashing through the station. And so these have a long history and are highly reliable. If you didn't have those and this curb anchored to the building and something got loose, well, the whole machine would be out in Central Park. Now, this is the end of my slides. The building got built, It was dedicated in 1977. I think the topping out was 76. Received a lot of publicity. Became a favorite building in New York. People like to go there because there are restaurants and recreation things of all kinds in the lower floors, and it's very convenient. There's a subway line that enters right in the corner. And so I think that's the end of the slides, and I'd like to have the full lights now. But so far, we've got a building with an unusual degree of structural elegance, I think, and simplicity. And the first tall building in the world ever built with mechanical help to make the structure work. That's remarkable. Incidentally, that has been now copied 100 times in Japan, and we did the same thing in the Hancock building. We were hired to correct some motion problems there a few years ago. But this is ubiquitous, and when I go to Japan, I'm treated like a tin god because I'm the father of the tuned mass stamp. I said, really? Well, in the spring of 1978, May, I was with the architect in his office, and we were planning some new buildings, some new towers to be built in Pittsburgh. And we had a meeting with the U.S. Steel representative, and we planned to use these diagonals all over again. They saved so much money, and the architect actually liked it because there's much more open space when you're inside trying to look out. The man from U.S. Steel asked, how did you make the connections in the field on these diagonals? I said, I know how we made them. We welded them, full penetration welds. He said, you did? He said, that's terribly costly, hard to get reliable welders. I don't think we would want to do the job if there were full penetration welds. And these are humongous steel column sections. So I said, well, I don't know. I know it got done. I called we had a branch office in New York at the time, and I called my partner down there, and I asked him, how did they work out? He said, well, didn't you know? Bethlehem Steel, who built the building, came, and they offered $250,000 back to the bank if they could redesign a different way of connecting these things. Not just because finding the welders was difficult, but the whole process slowed down the erection of the building. And they said, we don't think you need all these full welds. We understand these members are in compression, and they need to be connected up for the difference between tension from the wind and the compression that's in there. Of course they were in compression. That's why we put them that way. So this was a perfectly reasonable request. And the office proceeded to think this through. Bethlehem Steel actually designed beautiful bolted connections for the forces that my people gave them. And that was that. The building went up and smoothly, and everybody was happy. June 1978. I'm in my office. I got a call from a student at I do not know the school. I wish he would call me. From the past, he never has, but anyway, he was a real student from New Jersey. I think he was an architectural student, and his teacher had given him this building to study and report on because it's unusual. And his teacher said to him, that engineer didn't know what he's doing, and nobody should put the columns in the middle. They should put them in the corners. That's silly. And I told the student, I said, well, your professor's full of it. He doesn't understand the problem we had to solve because there was a church in the corner. So this whole structure developed to accommodate a special problem. And then I got into a little study talk on the phone. I actually called the student back because I couldn't talk to him continuously when he first called, and I called him back and pointed out to him that there's some peculiar things about this building. And you have a little picture. Don't look at it now, but study it at home tonight. And you'll see that when a conventional building has 4 columns in the 4 corners, the worst loading case is when the wind is on the diagonal, believe it or not. And in our building, the worst loading case was not the diagonal, but it was this ordinary wind that everybody thinks about. The wind pushes straight on the building. That was the critical case. So I said, you tell that to your teacher, and then you'll have something up on him. Now that night, or afternoon later on, I sat down and made a few drawings, almost like the one you have in the end of your handout there, that said, well, let's think about the effect of diagonal winds on every aspect of this structure. The one that really concerned me most was, did deflection make any difference? I should have known better. If you've got an absolutely symmetrical structure, beam symmetrical about both axes, right, the stiffness is going to be the same around all axes. But in order to prove that to myself, and since this wasn't simple beam, it had a lot of shear stresses, I had to go through the calculations in the diagonal forces. And I'm so old-fashioned, I can do it without a computer, you see, and do it by the method of virtual work. And when you do that, you come up with some curiosities. That when you put the wind on the diagonal direction of the building, I'm sorry about the confusion between diagonals, but we're talking about the diagonal direction of the wind, and now we look at the diagonals, the stresses in half of them vanish, and in the other half, double. Now, this is a very peculiar behavior. And suddenly a little light went on up here. I said, well, last May I heard that they had supplied forces to Bethlehem Steel for the connecting these tension forces, the difference between tension and compression. It would be a miracle if they ever thought that through, to think about the diagonal wind. It just wasn't in the nature of anybody. The mindset of people throughout the world designing rectangular buildings to look at it on the drawing, and the wind goes this way. So I had a bit of a worry. I didn't panic right away, but I decided to go down to New York to my office when I could get there, and it took a week or two. And I alerted them, guys down there, and I said, I would like you to get out the drawings, the detailed drawings of all these connections. And they had them all. They're called shop drawings. And let's go through the process of how these were designed. Well, there was no question. They had taken the straight-on wind, not the diagonal wind. But then it turned out they had done something else. Ooh. There was an argument between two guys in the office about interpreting the building code. And the building code, which was kind of an antique in New York at the time, said something about columns in tall buildings that get tension from wind when the building's leaning over. You should only subtract from the tension of the wind 3/4 of the dead load. But one of these nitpickers in my office said, well, this isn't a column in the building. It's like a diagonal in a truss. And they didn't say anything about that. So you can use the full dead load. Now think about that. If you've got 200 kips of tension from the wind and you've got 1,600 kips of dead load, you can subtract one from the other and you get 400. And the bolts were good for about 100 kips each, so that would take 4 bolts. If you took only 3/4 of 1,600, which would be 1,200 away from 2,000, you get 800 left, and you need 8 bolts. So just that little thought process, which had nothing to do with the diagonal wind, got too few bolts in the first place. And then you now find out that the wind force are going to be up like 40% more due to this diagonal behavior. I said, this thing is in real trouble. Now, there was only one thing only one more straw I could clutch at, and that was to fly up to Canada and get the wind tunnel people to retrieve all the data they had, which they had on magnetic tape, and they had all the computer skills. They could answer me the question of what is the maximum probable force in 100 years or any time period on any one of these diagonals in the building. And I went up there, and they had the data, and it was even worse. Some peculiarity which I don't understand to this day, in the dynamic response, things gang up from time to time at peaks that are a little more than the geometric simplicity of fluid and laminar flow. So anyway, the forces went up 60%. I collected all the data from them, trying to keep my cool. I had all the data on every one of these joints. Went home, went up to Maine, went to my little island which we own, and isolated myself for 3 days. My wife was there, calculated away. What I wanted to know was when was this building going to fall down? I found out 2 things, because I had data for both circumstances. If the dampers were working, they made an enormous benefit. But if the dampers failed because the storm knocked the power out, and you had to rely on that structure by itself, the return period to failure was 16 years. Think about that. What does that mean, return period? I don't know, 50-50 chance that such a storm will come in 16 years, I guess. Statistics are not my forte, but anyway, essentially, that storm was going to fall down in my lifetime. And since this was July, it could fall down the summer of 1978, because the hurricanes are going to be what does it. So, what do you do? Here I am, the only man in the world, only person in the world who knew this. My friends up in Canada were so professional, they would keep their traps shut forever, so here I am. There's nothing wrong with the building. Nobody knows anything's wrong. There's no cracks. There's no building behaves itself perfectly. So, what do you do? Well, first of all, I did sit down and say, how would I fix it? You could fix anything if you think hard enough. And one of the nice things about this story was that these diagonals, because the architect didn't want to show them on the outside, they were set back from the glass line so that you could even draw curtains between the glass and these things. So they're freestanding sculptures, if you will. Some people hate them in the building, but anyway, they were quite accessible. And the connections were made above the floor so that the workers doing the bolting could get at these connections, in most cases, easily. So they were very accessible. And it was easy to see that you could plant big steel plates 2 inches thick and 6 feet long, like Band-Aids, literally Band-Aids, on both sides of these joints. All you had to do was open them up and get the material, and weld, and you could build all the strength in the joint that you needed, because there was never any question about the strength of the members themselves. The question is, how do you mobilize people to get this done? And what's going to happen to you? Well, I went home, back to my office, told my wife, I said, we're going to have to solve this problem. Now, if you read the New Yorker story, it says I thought briefly about driving into an abutment. But and that's true. But then I said I would miss the end of the story. So I got back to the office and started thinking, what do you do first? Well, I got to call my client, who was the architect. Turns out he was in California and was taking an extra day, non-business day. The secretary didn't know how to reach him. Oh, God, we got to move. I called his lawyer and said, you got to represent the architect because I can't act on my contracts with you. And he said, oh, no, no. Well, finally he agreed to meet me. And he gave me the best information I could get. Now, you have professional liability insurance as an architect or an engineer these days, unfortunately. And so first thing you do, he said, you call your insurer first. Don't you take any unilateral action. You might cut yourself off from your coverage. So we called the insurer, which was out in Chicago, but they had lawyers in New York. The lawyers called me back, said, be here tomorrow morning at 9 o'clock. Don't you speak to anybody in this world. They called me back later in the day and said, we're going to have another engineer here to listen to you. They thought I was nutty. Nobody in his right mind calls up and says, my building's going to fall down. When there's no visible evidence of distress. So anyway, I rejected the first engineer, who shall remain nameless. I mean, he was a perfectly competent man, but he didn't know enough about tall buildings, or particularly wind. So I said, why don't you get Leslie Robertson. Now, Leslie Robertson is a very famous man in this world. He was the one that designed the World Trade Center towers. He knew a great deal about damping, wind tunnels. And I figured that I didn't want to horse around. I wanted to get the best critic of my own thoughts, as a matter of fact. So I went to New York, talked to the lawyers for an hour, and then they brought Les in. Les listened to me. The whole problem is so simple if you think about the geometry and so forth. It doesn't take more than 10 minutes to realize that this is a disaster. The wonderful thing that happened then was that the insurance company said, we can't wait. We got to do something. No, wait. You have to do something to measure. Am I empowered to do something? Yes. Call up the bank. Let them know. Tell them how we're going to solve the problem. See what they do. First, I had to go back to Cambridge and get Mr. Stubbins, who flew in that night from California, and sit him down in his house and mix him a martini and get him calm. And the lawyer was there with me, and we told him, you know, our building's going to fall down if we don't fix it, but don't worry, Hugh, we're going to fix it. I said, you have to come with me tomorrow morning. I got a ticket for you on the plane. We could get first-class tickets to New York in the old days. And we're going to try to call Walter Wriston. Well, I don't even know who Walter Wriston is, but he was the most powerful financial person in the world. And he was the chairman of the board of the CityCorp Corporation, which is, you know, multi-billions. And I had met him once, but the architect always has more contact with the high mucky-mucks than the poor engineer. Anyway, he came down, Stubbins came down to my office, and we started to call on the phone. Now, you don't call Walter Wriston and expect him to jump for a meeting in the next 20 minutes. You might wait a month. Well, what will we do next? Well, there was a wonderful man who was a senior vice president at the time we were designing the building, and he had spent some time here at MIT at the Sloan School. He had a good deal, I don't know, rub-off knowledge about engineering and mathematics and one thing and another. And so when the decision on whether to even put that damper in the building had to be made by some high echelon person, they called him in. And his name is John Reed. And today he is the chairman of CityCorp. But he was chairman in waiting even then, I found out. So he did agree to see Hugh Stubbins and me. He said, "I'll give you half an hour." I went and talked to him, told him the whole story. I said, "I need your help. I have to have this at once. We have no choice in this matter. And here's a solution. This is how we can fix it. But you have to mobilize the forces. Only you can do that for me." And he said, "How much is it going to cost?" "I don't think it's going to cost an awful lot. $1 million or $2 million. That's nothing for a building that costs $175 million, and if it falls down." So he kept his cool. I mean, he's a great guy. And he said, "All right, you go back to your office and wait for further communications." And my office actually happened to, by chance, to be 1 block away. So Hugh Stubbins and I went over, and then I had other people with me. And Robertson came too, I guess. He wasn't at the meeting with Reed, but well, we had lunch. Finished dessert. My secretary came over and says, "Walter Wriston is coming to our office in 10 minutes. Can you imagine that? So he did, and he turned out to be a wonderful fellow. And the story was repeated to him over again, and he said, "Well, I guess we have to act, don't we? What am I supposed to do? I guess I'll have to handle the public relations. And I'll have to handle the relations with the people in the building." There were people in the building and tenants in the building, and you got to communicate with them. No, we had to cook up a line of bull, I'll tell you. And white lies at this point are entirely moral. You don't want to spread terror in the community to people that don't need to be terrorized. We were terrorized, no question about that. But I had gotten a little piece of knowledge up in Canada from a guy that when I was up there, and this hurried mission, and they said, we have had more data developed on the wind velocities in New York since the original tests were done in 1970. This is 8 years later. And we have found that the probable wind velocities are a little bit higher in the 100-year storm. Thank you very much. So we passed out that as the light of bull. That Lemessurier had found there was new data, and he has recommended to CityCorp that in a rather minor effort, they can bring the building up to survive a wind load of 1,000 years. That's what actually got printed in the press. Many of you may have read this New Yorker story. The greatest thing that happened, no, I'm getting ahead of myself by, no, not far. These press releases went out in the tabloids at night, more or less what I've said. I had to set up headquarters in New York. And I had a nice guy in my office whose cousin was the night manager at the Waldorf Astoria. I said, I need a suite with 2 bedrooms and baths, because various people are coming and going, consultants and so forth. And so he called me up and said, well, you can have Frank Sinatra's suite for a month. That turned out to be quite comfortable. My wife came down to answer the phone, and when I got back, she said, well, Bill, the New York Times called at 5:15. Uh-oh. I called the lawyer in Boston. I said, do I have to talk to them? Look, if you don't talk to them, they'll smell a rat. You've got to do something. You've got to try. And so I mixed a martini for myself. And it's 6:01. I dialed the New York Times. I pick it up, the phone. They pick up the phone. It's a tape recorder saying, the New York Times has gone on strike as of 6 o'clock. Not only did the New York Times go on strike, but all the newspapers in New York went on strike until October. So we had a press blackout, and that was the greatest thing that ever happened. Television was never awake at that time. They got their information first from the newspapers in those days. So anyway, nobody ever knew what was going on except the few people directly involved. No, we got mobilized very quickly, and within days we were welding. And this process went on really quite an orderly way. I stayed down there all the time. It was a constant calculation trying to figure out which joint to mend today or tomorrow to be ahead of the game in the return period to failure. The other thing I did on the very first day was to get the power lines brought in to run that damper around the clock, and we got 3 experts from Minnesota, from the people who had made it, and they stayed there like nurses. 24 hours a day, there was somebody there to change a valve or do anything that needed to be done. I mean, I didn't expect it to break, but good heavens, you got a whole building riding on it. You don't take any chances. So all those steps were taken. Les Robertson was initially, I arranged with the insurance company to make him my consultant. The bank said, well, now, there's 2 guys. We don't have anybody on our side. So Les and I worked it out that I would release him from being held to me, and he became the representative of the bank. So the 2 of us then. But he really, I must say, he did not believe in my damper. He said, I formally can't believe in your damper. I have to take the idea that this building damper will not work, and if the wind comes and the storm is coming up here from the Caribbean and we aren't fixed yet, we have to evacuate the neighborhood. This building is 900 feet high. Sometimes I've talked about this, and the title of the talk is Why CityCorp Did Not Fall on Bloomingdale's. Bloomingdale's is 4 blocks north on Lexington Avenue, you see. The blocks are only 200 feet, so the top of it would fall right on Bloomingdale. I stayed out of the loop except on the final panic button loop, but there was a whole protocol set up by approaching the mayor's office, talking to all the security people in New York, police and special people. There was a whole contingency plan of who called who and how this would happen, and the police would evacuate 10 blocks around this building, which means thousands of people. The Red Cross was ready with 2,500 volunteers to be called at any moment to shepherd all these homeless out, find places for them to go. There was a big storm coming. There was 3 different weather services hired, constantly making reports every day. A little rumble down there in the Caribbean, so forth. There was one funny thing that happened. This building was so symmetrical that Robertson got electric strain gauges on all of the 8 diagonals on one floor, which wasn't yet occupied by a tenant. So you had a perfect way to measure the forces on the building at any instant. There was no other place for the forces to go. So this was piped into his office, and there were tapes made all the time, recording all these things, and nothing much happened, except they came into the office one morning and the thing gone off the chart. What's happened? We didn't hear of a storm last night, did we? They made a very great tactical error. They brought some experts from California flown in to put these strain gauges on, who never thought that they should hire a New York union electrician. So the union found out electrical work was done by non-union people. They went up and snipped the wires. So the building went off the chart. Anyway. Well, I had a lot of fun. Once it got going, the exhilaration was quite something. To see that little old country boy from Cambridge could start such forces moving. Everybody was absolutely wonderful. We had a big meeting with the city of New York. Les Robertson said, and he was very correct about this is the first thing you must do on anything like this. You have to let public officials know. You don't want them to hear about it secondhand. They'll hold it against you forever. You have to put them in the know before somebody calls them up. So we got in touch with the head of the New York Building Department, and there was about 6 people from the department left their office and came over to Robertson's office, and the contractor and I went down, and I simply told them the whole story. Of course, they didn't have any choice. I mean, what are they going to do? They turned out to be very nice, wonderful. They said, gee, if everybody behaved this way, we wouldn't have to have a building department. So that's true. Am I doing something wrong? So the crunch finally came at the end of the summer. You've read the story perhaps, but we had this hurricane watch all the time. And really, it was the most calm summer that you could imagine. But as Labor Day weekend was approaching, which is the end of August, 1st of September, this storm was coming up the Atlantic. And on Thursday night, it really became quite serious. See, the one storm that would knock this building, Galley West, would have to come right up the Narrows, and the eye of the hurricane would go up the Hudson just a little bit to the west of the building, so you get the full southeast winds head on. That's what you have to worry about. It's a rare event, but here was one that had within its track record, I mean, in the track records of things like that before, it could happen. So there was a real panic on Friday morning, the beginning of the Labor Day weekend. I canceled my trip to Maine and so forth. We had to sit there and say, the people actually all talked to me. They gave up talking to Robertson because they began to believe me that maybe the damper would save the building. So if the damper is running, what storm can we stand? I said, we can stand a 200-year storm now. Still didn't make anybody feel good. But by noon on Friday or thereabouts, we did get a call from the weather services. This storm is moving out to sea. And it did. And so I had a good night's sleep. And the next morning, Everybody else had left New York, and holiday, Labor Day weekend, I had it all to myself. It was rather boring, but that's all I needed. And so I got a taxi to drive me up to the cloisters, which is a marvelous medieval cloister that one of the Rockefellers built up on the shore of the Hudson, upper part of New York. I'd never been there before, but I'd heard about it. And so I sat in the cloisters and basked in the nice, beautiful sunshine, because you know, when a hurricane goes through, the sky gets clearer the next day than you ever see it again. And that's really the end of the story. Now, wait a minute, there are a couple of more things here. Who paid? My insurance company was really fantastic. They knew perfectly well sooner or later somebody's going to come around claiming, want some money. There are two questions here. Did we do anything wrong legally? And the one defense for any kind of professional error is, have you done everything as well as your peers would have done? And there are a lot of people, very specialists in this area, who gave that a lot of thought and said, this is the most defensible case there is, because nobody and his brother would ever look at the diagonal winds. That's just not in the mindset. And so, well, I don't care whether it's defensible. I didn't want to go to court. But I got my insurance company to give me what I call walking around money. We had a joint venture, you remember, and the 50-50 liability, and even if you didn't do anything wrong, which my partner didn't, he still has to pay if things go wrong. So he had only $1 million of insurance, so we had something more because we were a bigger company at the time. But I said, okay, give me his $1 million and take $1 million out of my pocket, insurance pocket, and give me $2 million and let me settle, please. You lawyers all stay away. I did. One meeting with the bank, and they all grumbled. And I let them know that, you know, we can fight this out in the court and we will win, we think. But I don't want to fight it out in the court, and I'm offering you $2 million. So one more meeting, and the lawyer went with me to sign the papers, and that was it. So we really had no contention in the end that it was a very serious matter. At the end of that year, the insurance company called up my office and my second in command, who was a retired Army colonel, and he handled all these difficult things. And they said, well, we're going to have to raise your premiums after that mess. He flew out to Chicago, where the headquarters were, and he gave an impassioned speech to them that said, not only should you not raise our premiums, you should lower our premiums in return for our behaving ourselves so well and preventing one of the greatest insurance disasters of all time that might have happened. You know what? They did. So, well, all well that ends well. I had to keep my trap shut for 17 years. I've talked about this from time to some of my students, and I've talked about it once at the University of Texas to a group of engineers, and I've talked about it at a hidden, sequestered conference in California where a group of people got together and everything was off the record. There were no tapes and nothing like this going on. And I began to realize that people were deeply interested in this story. I did not seek the New Yorker writer. He sought me. He found out about it through a grapevine and finally approached me about 3 years ago now, almost. And I checked him all out very carefully. But I think he's a super guy and a very experienced writer all his life. And we spent several days together, and I gave him all of the documentation that I had, which was very well done by my colonel aide. So we have memos of every hour, every day, all that summer of who was doing what and where. And I think I'm being authoritative. So that story came out. And as a result of that, I'm here. And I've enjoyed your company. I'd be happy to answer questions. do your homework, but you don't have to give me any papers in return. Thank you very much.
Questions for our speaker?
Don't be shy. Yes, sir.
Years ago, my father told me the story of Samuel Insull installing the first steam turbine electric generating station in Chicago. And when the time came to turn it on, Mr. Insull said, "I want to be there." And his subordinates said, "What if it blows up, Mr. Insull?" And Mr. Insull said, "If it blows up, I blow up anyway, so I'm going to be there."
Very good. I love it. Yes, sir.
What is your opinion about the number of other buildings out there where people weren't quite as responsible as you?
Well, there are some. I can't tell you where they are, because that's a secret. I have some very good friends in the engineering profession, and some of them have sought my advice from time to time, and there's a building in a major city. I think it may be going to get fixed, but it is a very important building owned by a very important national corporation. I'm not going to give you any clues where the city is. It's not Boston or New York. But anyway, it was designed by perfectly competent engineers who, because the code didn't say they had to do it, actually never even calculated the deflection of the building. Can you imagine that? There was some storm experience in this building, and it actually behaved pretty well, but it scared everybody. The only reason it behaved well, it was in the lee of another building. If the storm had come from another direction, it would have been down. 50 stories. Totally under-designed. Second order effects in spades. It wasn't the diagonal wind problem, but there are all kinds of problems. We already had one here in Boston, you know. The Hancock building got fixed, whole new structural frame in the wrong direction. That's another story. But Bruno Thurleman, professor of structures at Swiss Technical Institute in Zurich, was hired to review this building. Forget the codes, put all of science on it. He was the greatest man in the world on failure mechanisms of steel structures. And he almost came to bless it because he had an extra 3 months to kill between the time he made his initial report and the board meeting. He being a rigorous fellow, looked at the building in the wrong direction, and that's where the trouble was. And he said, this building will not survive the 100-year windstorm. Now, this was not designed by irresponsible people. It was designed within a paradigm for designing tall buildings, the same one that had been used for the Empire State Building and every other building. But when you build a building this long and that narrow at one end, you run out of the range of experience with that paradigm, and so it got a new frame. Frame was doubled. The stiffness of the building was doubled. No, there are a lot of them out there. Of course, the old buildings, I mean, the Empire State Building would never have stood for a minute if it didn't have stone walls all around. You know, that building was studied when it was built, and people actually calculated way back in the 30s what the period of vibration of the bare frame would have been, and it was going to be about 17 seconds. That is over the hill, I'll tell you. You measure the building's period of vibration, today even, and it's 3.5 seconds. Well, where's all this stuff coming from that gives you that extra rigidity? It's coming from the partitions and the concrete around the columns and the stone walls and stuff. The frame isn't even working there. Yes, sir.
It's my understanding that as a result of the Northridge earthquake, that there are some problems in Los Angeles with welded structures and some issues about how to face up and what to do next. Would you care to comment on that?
Well, you're absolutely right. In a way, that Northridge earthquake was a gift from the Lord because we had so much data out of it. One of the most interesting buildings, you know, the Getty Foundation has got a huge building that's been under construction out there. And the Getty Foundation has $1 billion worth of artwork to put in the building. So they had a lot of their connections crack in the steel frame. They weren't even finished buildings. But they also have a lot of money. So they gave, immediately, within weeks, they set up a whole research program at the University of Texas in Austin, which has some of the best testing laboratories. We don't have them at MIT anymore, but for full-size structures. Anyway, and they reproduced these failures with the same kind of connections with dynamic testing. And then they figured out what to do to make them better. So I think there are solutions that are known. How do you get at older buildings to do all the fixing? It's not simple. But at least for the next round of earthquakes, I think we know how to do them better. And those connections in the Getty Museum are taking advantage of this knowledge. This means welding supplemental plates on top of the flanges of a steel beam where it abuts a column so that the ductility happens not at the joint but out in the beam. The beam itself is the weak part.
Is there a possibility of a secondary failure where the end of that lap joint weld takes place?
I don't think it's quite that way because that's tapered down in a way. Anyway, they've proven with the same test that reproduced the first factors that this doesn't fail now. Yes, sir.
This is sort of a difficult question, but the process you went through and the story you presented for us today, is there a way to put that into the academic curriculum?
You've got it right here on tape.
Okay, yeah. Otherwise into the classroom.
Well, I've been doing it all my life. Not this story particularly, but I teach regularly architects at the Harvard Graduate School of Design, and I think it's terribly important for them to understand that nobody's perfect, and they'll never be perfect, and you have to face up to these things in small ways all the time. So I tell them this, and I tell them how to behave, too. I had one student came to me a couple of years ago. He said, I've been through 4 years of college and 4 years of graduate school, and nobody in academia ever told me how to behave before. I think that's pretty shocking. Now, I'm sure that's not true at MIT, but now I'm very firm with him. I said, look, if you got a license from the state and a certification from the university first, and now you're going to use that license to hold yourself out as a professional, you have a responsibility beyond yourself. If you see something that is a social risk, good heavens, this thing would kill thousands. You must do something. You must do something. I don't have such great pretensions about myself that I had the time to think that all through. I'm also selfish, you see, and selfishness sometimes is a good thing to have. This was my building and my creation, and I am very proud of it even today. I mean, there's nothing wrong with the design. It's elegant. It's like my child. I have to save it. It's automatic.
Any other questions? In that case, let's thank our speaker again. And all right, we'll do that.